Greetings, everyone. Let's talk about linear inequalities. So at this point, you should have at least gotten a treatment of solving linear equations and all of the different varieties of solving methods that we have for those, so that we can actually apply them now to also the inequality symbols. Before we get there, though, we need to talk about the differences, and we need to talk about the word solution. Okay? So, first of all, what is an inequality, right? It's the same kind of thing as an equation. It's going to have two sides. Well, most of them, the compound inequalities will have more sometimes. But for the most part, they'll have the two sides, right? But they'll be involving any of the inequality symbols instead of the equal sign, right? So less than, greater than, less than or equal to, greater than or equal to, or not equal, or those, okay? So, let's talk about the differences in solutions here. And don't forget, solution is a value that causes a true statement, right? Solution is any value that causes true statements. So when we were doing the equations with the linear equations, we were getting one solution at most, and that's because it's just x to the 1, no variety, and x is some number. And then we had a couple of special cases where x could have been no solution because of weird circumstances, or we also had the very special circumstance where x could have been any number, and we had ways of symbolizing that too. Okay, so now we're going to talk about the differences with equations and inequalities. The equations, as we just said, have a single solution for linear equations. What would that look like on a number line graph? Well, if I were to graph it here, x equals 4, that would be me putting just a solid dot on the 4, on the number line there. Okay? Because that's it. It is a single number. It's not even, I guess it could still be considered a set because you can have a set of one number. You can even have an empty set, but typically we don't even think of it that way because it's a single, right? However, an inequality, x is less than 4, for example, is an entire list of numbers. In fact, it's a humongous list. It's an infinitely sized list. Think about it. What's less than 4? By definition of less than, it would be anything to the left of 4 on the number line. Okay? Now, don't get the word less confused with size. All right? The entire list of negative numbers are less than 4. So negative 2 is less than 4, negative 10 is less than 4. That's all true because they're all to the left of 4. So I've got this whole list of values that come along with this statement here. Okay, well, so we have many ways of displaying this. You'll notice you never really graph like this with equations. That's because it's really not necessary. If you don't have one solution, you either have none or you usually have countable many, like 2 or 3 or 4 solutions, and you just list them out. With inequalities, typically you won't. You have entire sections that we call intervals. An interval on a number line is a connected list of points, a connected list of numbers on the number line. Okay? So, x is less than 4 is one big interval, one whole section, it's all connected, to the left of 4. If I were to graph it, old school graphing would have you do it like this. It would have you put an open circle on the 4, and it would have you shade everything to this side here. Okay? So, I do the graphing so that I can visualize what this is saying. That's another way that we post our solution set for an inequality. We don't always stop at the inequality like we would an equation. Okay, the inequality symbols are great. They do symbolize everything, but sometimes we need that visual side. right? So I'll also graph it. So when someone says graph an inequality, they mean draw a number line and shade an interval on it. Okay? So then what would be the difference with less than or equal to 4? Well, in that case, I have to also include 4 as one of the actual answers. And that's where I did not here, you see, because 4 is not less than 4. But 4 can be less than or equal to itself because it hits the equal portion of it. So old school would be to put the solid dot like up here and also to shade everything to the left of it. Like so. Okay, now I keep saying old school, right? There's newer versions, and typically you'll see this a lot more, especially on the online homeworks and things like that, where instead of the open and closed circle, they'll use parentheses and bracket. And that has to do with the next thing that we're going to talk about in just a second, but it's to line it up with some of the terminologies that are used more commonly. And that would be like this. I would put a parentheses to where it would just barely hit the number 4, right? This would be a round parentheses, and I would still shade. Whereas if it's the equal to, I would put an actual square bracket actually on the 4, and then I would still shade. Okay? So parentheses for not equal, bracket for equal. And that has to do with the interval notation stuff that we're going to talk about. With 2D graphs, they still do the open and closed circle because of the multiple dimensions that it may have. But on a number line, typically they'll start using the parentheses and the bracket. They're easier to draw, they're easier to get by with. And it looks a lot like the symbols that we're already using for the other piece. Okay? So one of the things you may have to do in any given inequality is graph it, the solution set, as an interval on a number line. Don't forget, interval means connected list. Okay? You can have more than one interval as a solution in your solution set, but that just means that it's broken like maybe into 2 different sections. If it's all one section, that's one interval. Okay, so then that brings me to this right here. Interval notation. The way we write is what notation means, right? The way we write intervals. So this is a third way that we display a solution set to an inequality. And it begs off of the fact that intervals must be connected lists. Okay? So if they're connected, then really all I need to know is where does it start and where does it end, because then everything in between those two is implied. It's an interval. It's connected, right? So that's what interval notation is. You list a starting number, you list a finishing number, and then you just have one more thing to put on either side, and that is, are those endpoints included or not, right? Because notice sometimes we include the number, and sometimes we include the number and sometimes we don't, right? So on either side of my interval notation, right, I'll have numbers in here. I'll have either fully open. I could have left side closed, right side open. I could have right side closed, left side open, or I could have a completely closed interval. Okay? It just depends on the situation that you've been handed. All right, so on the interval notations for these, right, there is no interval notation for x equals 4. It's not an interval, right? It's not a connected list. It's a single number. In the case of something that's a single dot like that, you may have to list it like this. But this is not called interval notation. That's called set notation with the squiggly braces. Okay, so interval notation, though, I do have a connected list here. I have to list a beginning number. Well, it's shading to the left forever. Well, what's the forever number on the left-hand side of the number line? That would be negative infinity, right? Negative infinity is on this side. And I would put a parentheses on that because you can never include an infinity. Never include infinity because it's not actually a number I can land on. Comma. Where does it end? It ends at 4. In this case, it's not equal, so I would leave that open. So I have a completely open set. In this case right here, I would again start with negative infinity, because that's the left-hand side, and it would go all the way to 4 again, so 4 is my ending number. And in this case, I would put the bracket there, because the 4 is actually included. It is actually equal to 4 in this set. Okay? So there's 3 different ways in any of these inequalities that you're going to be asked to list the answer. The inequality itself, a graph on a number line, or the interval notation that represents the list in interval form. Time to put some of those solving techniques into action and mix in the ways that we display the inequalities. Okay, so I've got 3 examples here for you. Let's start with the basic one. Okay, so just like with your equations, I want letters on one side, non-letters on another. And since this is linear, I can easily combine like terms. Don't forget, I know it's linear because it's x to the 1, x to the 1, right? Okay, so letters to the left. Even more important in inequalities, letters to the left. Because if your letter's on the left-hand side, your inequality symbol is much easier to interpret. Okay, so I'm going to start with that. I'm going to add an x so that I don't have this x anymore. Next, I'm going to subtract a 5 so that I don't have this anymore. Remember, the idea is to get rid of the obstacles here. So I'm left with 4x is greater than or equal to 14. And I'm going to divide both sides by 4. I'm going to point out here, and I want you to notice that I'm dividing by a positive number. That will be important for you to realize in a minute. Okay? Dividing by a positive number has no effect on the inequality. So I have x is greater than or equal to 7 over 2. All right. So then I need to display this in the other 2 ways. I need to graph this inequality, and I need to give the interval notation. So to graph it, pretty straightforward. I just need a number line. I need to know where 7 over 2 exists. So don't forget, if you divide that out, 7 divided by 2 is 3.5 or 3.5. So what I'll do on my number line is I'll put down a few numbers that are around it, like so. And I know 3.5 is right here. I'll just put a bigger mark here. And I'll just label 7 over 2. This is greater than this time. X is greater than, which means all of the numbers to the right of. Right? That's what greater than is actually mathematically defined as. All numbers to the right of on the number line. And it's equal to. So one way to do it, of course, would be to put the solid dot and shade to the right. The other way would be to physically put a square bracket and shade to the right, just depending on your instructor or whatever way you're doing with this, or the homework system. Both of them were technically correct. Okay? That's a solid dot, not an open one. The interval notation is going to be listing a beginning number and an ending number. It begins at 7 over 2, and it ends never, so infinity, right? Positive infinity this time. Of course, I can never include an infinity, so that gets an open. And 7 over 2 had the equals, so it does actually get a closed. Okay? So I've got the graph and the interval notation there. Next example, I've got something that I need to manipulate and consolidate some pieces here. So let's do that. I'm going to use distributive property. I'm going to combine like terms. The 3x and the negative 8x give me negative 5x. I'm going to add 5x because I don't want this one anymore. That causes me to also add 5x over here. And I'm left with 10 is greater than 3. Well, we've run into this kind of situation back with linear solving, remember? We talked about what happens when all of your variables go away. You need to evaluate the resulting statement. In this case, the statement is 10 is greater than 3, which is true. 10 is further right than 3. And remember, if it's already true, that means x didn't have a say in whether it was true or false to begin with, and that means all numbers. Right? So if I were to graph that, I would just be shading the whole number line. Okay? And then the interval notation for that would be negative infinity to infinity. Don't forget what we're saying here with these statements is we're giving sets of values that cause true statements, right? That's what a solution is. So if I were to pick any number from this interval, right? Pick 5, it's in the interval, and plug it back into the original statement, it will be true, right? 3 times 5 is 15, plus 5 is 20, and 19 minus 5 is 14. 20 is greater than 14. True, right? That's what these sets represent. They're the list of values that would make the original inequality a true statement. Okay, so what happens if we have fractions? No big deal, right? We've handled this. How do we get rid of denominators? They're made with division, so we use multiplication. 9, 6, and 18. I'm going to multiply by 18. And again, I'm going to point out that 18 is positive. Multiplying by a positive number in an inequality doesn't change the inequality. We're going to talk about what happens when you multiply by a negative in a minute. 18 divided by 9 is 2. 18 divided by 6 is 3. 18 over 18 is 1. And 1 times 18 is 18. I'm going to use distributive property. Whoops, made a boo-boo. Less than. Use distributive property. 2x plus 8 plus 3 is less than x plus 18. Combining like terms that are already on the same side. Okay, letters to the left. And non-letters to the right. So minus 11, minus 11. Okay, so then that leaves me with x is less than 7. So then I need a graph and an interval notation. Okay, so on a graph, just quick and dirty, right? 5, 6, 7, 8. Just need a few numbers on there to give it some reference points. And then it's less than, so that should be everything to the left, but not including. So I would actually leave it open. Or don't forget, the other way to do that would be to shade everything to the left and put a parentheses on the 7. And then the interval notation, starting on the left-hand side, would be negative infinity. And then it would stop on 7, and 7 is not included, so it would be fully open. Okay. Real quick, though, I want you to realize that if I hadn't done letters to the left, this still would have been the statement that I would have reached. But if you do it the other way, you could completely end up with this statement, which is equivalent to this statement. Okay? And that's all right. But just the way we interpret, the way we read our sentences, the way we say our sentences, the way we think about our sentences, even in English, is that we like to have our subject of our sentence first, right? Unless you're a certain little green Jedi that likes to say things in reverse, right? Less than 7x is what this would say, right? Little Star Wars humor there. So x is less than 7 is just easier for us to think about because we like to have the subject of our sentence first. X is the subject. He's the thing that's doing the being of these sets, right? So letters on the left helps us interpret it better. It's okay to get this, but you need to remember that it's easier to interpret with the letter on the left like that, okay? Let's finish up this lecture talking about what happens when you multiply or divide by a negative in an inequality. And typically, this is only going to happen to you when you're dividing by a negative. We don't multiply by negatives across an entire inequality very often. But just keep in mind that it is actually the same thing either way. Okay? So let's get the examples with division in there, since that's what we'll be doing a lot of at the end of our inequalities. Notice if I have to divide physically by a negative, the negative is part of the division. And that's because there was a negative attached with the multiplication originally, right? Then the inequality symbol does reverse because the negative sign is doing the opposite of everything in the inequality. That's what division does. It's like a big blanket bomb. Boom, hits everything. Whereas just because there's a negative in the answer, right? Notice it's the same negative whether the negative's on top or bottom. The answer is still going to be negative here, right? If the negative is not physically part of the division process, it does not reverse the inequality. Okay? So don't think of it like, oh, it's a negative answer, I'm going to flip those signs. No. If there is a negative in the action part of the division, then you actually reverse. Okay? So you'll notice in all of the previous things we multiplied by positive numbers which had no effect on the inequality, and that's why I pointed that out. If I would have multiplied by a negative, it would have reversed it. Okay? Just like dividing by a negative reverses it. Let's get one example and finish it up. So I'm going to start by using distributive property. Don't forget to distribute the negative with the 5, right? Negative 5 times negative 3 is positive 15. Notice that did not reverse the inequality because I'm not doing a both sides statement. I just simply simplified each individual side. I'm going to combine my like terms. Okay. My x's combine here, my numbers combine here. And then I'm going to get rid of the things that are in my way of solving. So that means I want to subtract a 6x from both sides to get rid of this. And I also want to subtract a 15 from both sides to get rid of this. Okay. And then I'm resulting in negative 9x is greater than or equal to negative 20. Now, before we move on, let me point out, we just handled a bunch of negatives, and again, it didn't reverse because I did not multiply or divide by a negative to everything, right? Subtraction involves negatives, but that's not multiplication and division. So again, it did not reverse it there. However, I want x by itself here. So I'm going to divide by negative 9. Dividing by negative 9. So that will reverse the direction of my inequality. X is less than or equal to 20/9. Okay, now since this is an inequality, right, we finish it up by doing the other two formats of solution set. 20 over 9 is just a little bit bigger than 2. It's 2.22222, right? So I'll put a few numbers on here that are around that. And 2.2222 is going to be somewhere about right here-ish. So there's 29ths on the number line right there. Okay, it's less or equal, so I'll be shading to the left. And the equals means that I would either put a solid dot on it or a bracket, right? Either way. And then the interval notation would be negative infinity to 29ths. Okay? Now real quick, sometimes the interval notations, if someone's trying to be a little bit more fancy or a little bit more mathematical, they may actually put these in front of it. Okay, now if they put these symbols in front of it, all they're saying is that X is an element of this set, okay? Or X is a member of this set. It's the same thing as putting an equals on a single solution, okay? But this isn't a single solution, so I can't say that X is equal to the set. So don't put equals. We have this symbol for meaning is a member of, is an element of, okay? So just in case you ever see that, I'm going to demystify it there for you. And I hope this lecture helps you in solving your linear inequalities.